Welcome to the video on graph and network theory. So there's a couple of terminology bits and pieces that you're definitely going to need to make sure you've watched first. So do make sure before you go any further in this video that you have recapped all of the parts of a graph or a network, and that you are familiar with the terms that we're going to be using. I'm just going to jump straight in with the bits of this topic that are relevant for the questions that you're going to get. So the first thing we need to think about when we approach a graph and network theory question is that we need to know what the node order is. So the node order is going to be something along the lines of, and you need a working definition as opposed to an actual definition, something like the number of arcs from each node. So if you count up the number of spokes coming off of any particular node, that's its node order. So if I draw a little network here, it's got 5 nodes to it, and I'm going to connect up those 3 in a cycle like that, and I'm going to have 2 more on there. Then this central node here has a node order of 4. This top node over here has a node order of 2. There are 2 spokes coming off of it. Node order of 2 here, 1 and 1. So we'll reference node order a lot, and it might not be something you explicitly define, as I've mentioned, but you're going to use it an awful lot. Eulerian then is the types of graphs where all of the nodes are even. So all nodes must have an even node order. So that means that our graph at the moment, the one that I've just drawn, isn't Eulerian. But I could add a single arc and I could make it Eulerian. So if I add in an arc here, this node goes to node order 2, so does this one. I've got 2, 2, 4, 2, 2, all of them are even, and so now I have an Eulerian graph. Semi-Eulerian is that there are 2 and only 2 odd nodes in an otherwise even graph. So the graph we had before, 2, 2, 4, 1 down here and 1 here, was a semi-Eulerian graph because there was a single pair of odd nodes, and it's like almost there. It's almost Eulerian. If I add in that 1 extra arc, we get to an Eulerian graph. And then very particular to the way that OCR have started to be structuring their exam questions, this is particularly relevant if you are studying the OCR exam board, is that graphs can be simple and or connected. And quite often questions will start going, a simple graph is, a connected graph is. So just to recap, a simple graph then is one where there are no multiple arcs or loops. Can't spell this morning. Multiple arcs or loops. So a multiple arc, don't forget, is where you have more than 1 arc going between the same 2 nodes, and a loop is an arc that connects back to the same node. So as long as neither of those situations are going on, we've got a simple graph, and a connected graph is one where you can get from every node to any other node. So in a sense, there is a path between any node. I can start at any node, node reached by any other node. So they don't have to all be connected by direct paths, but there's no little node sat out on its own that you can't get to from any other place. Every single node in your network can be reached. So now that we've got some key terminology, it's worth us just thinking about some kind of key results that are coming out of our study of graphs and networks. So I wonder if you're noticing anything about the number of nodes and the number of arcs in a problem, or indeed the number of total node order and the number of arcs. So in this top graph that I've got here, we have one node of node order 1 and another node of node order 1. So my total node order is 2 and I have 1 arc. Here I've got one node of 1, a node of 2 and another node of 1. I've got a total node order of 4 and 2 arcs. So each little spoke, if you will, a line coming off of a node, is matching up with another line coming off of one of the other nodes, forming one single arc. So each 2 increase in node order corresponds to a single new arc. This is a really nice consequence. Basically, you can't have an odd number of node orders. You can't have a total node order that's odd. So total node order has to be even. Probably not the nicest mathematical way to write it, but there we go. Total node order has to be even. Otherwise, say you've got a node order of 21, you're going to end up with 10.5 arcs. You can't have half an arc. So that's always a really nice thing to keep in mind, especially when you're dealing with these types of questions. Then this is perhaps something to go and have a think about, but if you've got n nodes in a network, the minimum number of arcs you need to make a connected graph is 1 less than the number of nodes. We can just have a little think about a particular example. I would suggest you go away and think about whether or not you can prove it. To connect up a graph then means that every single node is in some way reachable by any other node. So I've now connected up 2 nodes here. I can reach from this first one, I can reach this second one here. I've connected up a third, a fourth, a fifth, a sixth. I don't need to go back because that would form a cycle. At these 5 arcs, I've connected every node into my network. And you can imagine that if you extend it 6, 7, 8, 9 nodes, you're always going to have 1 less than the total number of nodes. So that's that one. The maximum number is n minus 1 over 2. And the reason for that is, well, let's have a think. So this first node, I could connect up to 1, 2, 3, 4, 5 choices. The second node, I've already made that connection, but I could make 1, 2, 3, 4 connections. The third node, that one's made, so I've only got 1, 2 and 3 to make. This one I've only got 2, or rather 3, this one I've got 2, and this one doesn't have any. So I end up with a little sum, in this case for 6 nodes, 5 and 4 and 3, 2 and 1 would be the total number of arcs in that network. Again, there's a couple of really nice proofs for this. I'd suggest you go away and have a think about them. So one of the best ways you can get good at these types of questions is just to practice. I know we say it all the time in maths, but for these ones it really is. Get a question, try it, study the mark scheme, try it again, because there could just be little nuances that you're missing in understanding, and the more you practice it, the more you're likely to pick those up. This is a particularly grueling question, but that makes it absolutely lovely. This is from OCR. It was their 2016 D1 paper. It's question 4, if you want to go and have a look at the mark scheme on it. And like I say, it's probably one of the trickiest ones that I've found. As I mentioned before, OCR have a bit of a habit of presenting their questions with this blurb at the beginning. It's just talking about a simple connected graph. Don't forget those definitions about simply and connected. If you read these ones, you might get a bit confused, so just think about what you know. We've got Holly in this problem, and she says that she's drawn a graph with exactly 5 vertices, having vertex order 1, 2, 3, 4 and 5. I would really recommend just drawing yourself out, blank piece of paper, 5 dots on it, 5 vertices, 5 nodes. And we're told that the number of spokes coming out, the first one is 1, the second is 2, 3, 4, and 5. And we're being asked to state how we know that Molly is wrong, that she hasn't drawn a graph. Well, I've got a couple of options here, and one of them is to think about what I know a graph must have. And we mentioned earlier that a graph must have a total node order that is even. Well, given that I know the respective node orders or vertex orders, let's total up what I've got. So I've got 1 and 2 and 3 and 4 and 5. That's a node order of 15. Well, that would imply then that we would have 7 and a half arcs. That doesn't sound right. In fact, that isn't right. We can't have half an arc. We can't have a spoke just kind of going off and not joining up to another node somewhere. That's just complete rubbish. So we know now that we don't have a graph. So there we were just testing what we knew. That total node order being even, because that then gives you a total number of arcs, is really quite a key little feature, I guess. Next part of the question then. So Holly's drawn a connected graph with exactly 6 vertices. Okay, let's draw 6 dots on a page before we even start. And we're told that the vertex orders are 2, 2, 2, 2, 4 and 6. Well, that sounds legitimate, doesn't it? Because their total of that would be an even number. So we know we've got a graph there. We're asked to explain how we know that Holly's graph is not simply connected. Okay, so we need to test her graph against those two definitions. So connected is that every node will be in the graph, in the network. So there's no sort of little guy stuck out on his own somewhere. We're not just leaving one of them out on the side. We're going to have all of them in the same network. Simply means that you don't have multiple connections or loops. Okay, I think that we could probably have in a 6 vertex graph 4 nodes of 2. That sounds about right to me, and a node of 4. I want to focus on this node of 6. So 6, say it's this one here. We make 1, 2, 3, 4, 5 connections. So currently I have node order 5. Where's the 6th one going to go? It could connect up to one of the other nodes again, or it could connect to itself on a little loop. But either way, that gets rid of that simply connected bit. Because a simple graph has no loops and no multiple connections. So that's how we know that Holly's graph isn't simply connected. The 6 node order or vertex order, can't spell, there we go, implies we'd get multiple arcs or loops. And therefore not a simple graph. It's a connected one, but it's not simple. Okay, part B. Determine whether Holly's graph is Eulerian, semi-Eulerian, or neither. Okay, well, Eulerian graphs are ones where all of the node orders are even. Semi-Eulerian is where there's one pair of odd nodes, and neither of those is if both of those conditions fail, we're in the neither category. Well, I've got node orders of 2, 2, 2, 2, 4 and 6. They are all even numbers. Oh, hello. That was quite exciting, wasn't it? There we go. Therefore, even. So we've got an Eulerian graph. It's worth pointing out that Eulerian graphs don't have to be simply connected. That's a completely different idea. We're just testing that, and the one feature of an Eulerian graph is all even nodes. We're meeting a new character, hey! Ollie then, rather than Holly, has drawn a simply connected graph with exactly 6 vertices. Okay, great. So we've got our 6 dots again, and we know that this one is connected and simple. So all of them are going to connect up and there's going to be no multiple loops. We need to state the minimum possible value of the sum of the vertex order. So that's the total node order. What's the minimum value of the total node order? Right, well, we know that node order is linked to arcs. So if I could find the minimum number of arcs, I could find the minimum node order. We know that in a 6 vertex graph, 5 is the minimum number of connections to create a simply connected graph, because all of them are connected in now and there's no repeats or loops. So I know that 5 is my minimum number of arcs, and therefore the minimum total node order, or sum of the vertex order, is 10. We're then told that Ollie's graph is also Eulerian, so it's still simple, it's still connected, but it's now Eulerian. We're asking what values could those vertex orders take. Right, we know that they have to be even, so that's 2, 4, 6, 8, 10, so on and so forth, all the even numbers. We have 6 nodes, and we already know that if a node has a node order of 6 or indeed above, we're going to end up with multiple loops. So I can get rid of the 6 and certainly get rid of the 8 and the 10, which means each of these nodes here can only have a node order of 2 or 4, and that's it. Polly, clearly Holly and Ollie's friend, has drawn a simply connected Eulerian graph. Okay, so there's no loops, there's no multiple connections, everything is connected in and all of the node orders are even. It has exactly 6 vertices and it has 10 arcs. We know that. We've just got 10 arcs to fit into this thing. What can you deduce, so what can you say about the vertex orders in Polly's graph? Okay, so if we have 10 arcs, we know what the total vertex order or node order would be. The total node order would be 20. And given that we've got 6 nodes, we can probably slot in those 20 node orders into how many each one of them has. So I've got 6 spaces, basically. I've got 6 nodes, and each one of them we know could take the value 2 or 4. That's it. That's all we've got. And so I basically need 6 numbers of 2 and 4 that add up to get 20. Let's start with one of each, 2 and 4. That's given me a total of 6. Add another 4, that's 10. Add another 4, that's 14, and I've got 6 remaining, so I'll do 4 and another 2. It's about the only way you can make 20 out of those numbers. In fact, it is. So that's great. I know that my nodes are 2, 4, 4, 4, 4, and another 2. Part B, draw a graph that fits the description of Polly's graph. Okay, so 2 of my nodes need to have only 2 spokes coming out of it. Let's stick those ones at the end, shall we? So each one's on the end, they've got 2. They've got node order 2 there. This one's currently got node order of 1, so if I add in a line now, I've got 2. But I don't have a connected graph yet, so everything's got 2, node order of 2, but it's not connected. So I can connect in, so now I've got 2, 2, 3, 3, still not quite right. I've got 3, 3, 3, 3, okay, so one more, 4, 4, 4, 4. Brilliant. Just checking then, I've got a node order of 2, 1, 2, 3, 4, 1, 2, 3, 4, 4 again, and 4 again. Happy days. Except I didn't look too happy. There we go.